So, Samuel, we're diving into data loading for this lung cancer detection project, right?
Yeah, Alfred. Crucial step. Turning raw CT scans and annotations into usable training data.
This training sample sounds important. Can you break that down?
Absolutely. Think of it like prepping ingredients for a recipe. We need to transform the raw data into something our AI model can understand.
So, we're taking raw data. What exactly are we doing to it?
We're essentially cleaning and structuring it. We need to extract the relevant nodule information from the scans.
Nodule information? Like identifying the tumors?
Precisely. And ensuring the data is formatted correctly for our model. It involves a series of transforms.
So, we're not just looking for tumors, we're also looking for specifics about the tumors.
Right, like their size, location, and maybe other relevant characteristics. This structured data forms a sample tuple, which is the input.
So, is this data transformation always the same? Different kinds of scans or tumors?
No, it depends on the type of data. We might need to adjust the procedures. This chapter covers basic transformations. Complex cases might need advanced techniques.
This process sounds like it will take some time and potentially have errors. Any tips for ensuring data integrity?
You're right. Rigorous data validation steps are crucial. We need to check for missing values, inconsistencies, and outliers.
Wow! So, we're not just loading data. We're essentially transforming it into something usable for the model. Makes sense.
Exactly. This crucial step transforms raw data into valuable insights.
That's interesting. I'm picturing this as a kind of data alchemy.
Laughs, perhaps. Transforming something seemingly basic into something useful for our model. This step will ensure our model learns the correct relationships.
So, we're talking CT scans now, right? This raw data, how does it get processed?
Yeah, the raw data comes in these two files. AMHD file, holding metadata, and A.raw file, with the actual scan data.
And they're tied together by a series UID, right?
Exactly. A unique identifier for each scan, like a barcode, but for medical images.
Okay, so we get the raw data. What happens next?
Our program, CT class, takes those files. It figures out the 3D array. Crucially, it also gets the transformation matrix.
Transformation matrix? What's that do?
It converts coordinates from the patient's body to the image's coordinate system.
So like, turning a real-world location into a spot in the picture.
Precisely. Important for accurate measurements. We'll talk more about this later.
Right, this is all about precise positioning. And what about the annotation data?
That's from Luna. It tells us where nodules are in the scan. Plus, if they're malignant or not.
So, we know the nodule's real-world position in the body, and we can convert it to picture coordinates. It's like finding a spot on a map, and then figuring out where that same spot is on a satellite image.
Exactly. Then we crop a bit of the scan data around that nodule.
Why crop it?
To keep things manageable for the AI model. Too much data is noise, slows down processing.
Makes sense. And this crop piece gets packaged up with the nodule info, scan ID, and its place in the list.
Yep, just like PyTorch expects it. Our training sample, ready to go.
So, this whole process is about taking complex medical data and turning it into something a machine learning model can use.
Exactly. We limit the noise, focus on the relevant information. Crucial for accuracy and efficiency.
What about outlier data points? Those troublesome ones?
Yeah, we can use clamping to remove extreme values. Helps ensure data is well behaved.
Preventing unexpected results, right? And you said about handcrafted transformations. What are those?
That's called feature engineering. We could make some calculations, but usually the model will do most of the heavy lifting.
So we focus on getting clean, good training data. Crucial for effective machine learning. Okay, Samuel, so we're diving into Luna data. This candidates.csv file, what's its purpose?
It lists potential lung nodules. Think of it like a preliminary screening.
So, it flags things that might be nodules?
Exactly. It gives X, Y, Z coordinates and a class.
And that class, 0 or 1, is key?
0 means not a nodule, 1 means likely a nodule.
So, how many likely nodules are there?
About 1.
Right. So, candidates.csv tells us where potential nodules are. And annotations.csv?
This one gives us more details on the flagged nodules, like their size.
Why is size important?
Because nodule size can impact the disease. You want to be sure your training data reflects a range of sizes.
So, the size is crucial for preventing our model from getting fooled by only seeing very small or very large nodules in validation.
Exactly. If our validation set only has extreme values, our model may seem underperforming even if it is actually working well on a wider range of cases.
Clever. So, how many size measurements do we have?
Around 1,200.
So, we have more potential nodule data. How do we use this data effectively for building a model?
Well, we'll use the candidates to CSV to identify potential nodules, and then the annotations to CSV to get more specific details.
This sounds like a good way to make sure our model isn't just guessing on extreme cases.
Exactly. It's like having a detailed catalog of the lung nodules, some only possible nodule candidates and others well-defined.
Excellent point. Makes our training data more robust. This really helps us build a more accurate model. Thanks, Samuel. Okay, Samuel, so we're splitting data into training and validation sets. Crucial for supervised learning, right?
Absolutely. It's like having a practice exam before the real one.
But how do we ensure these sets are truly representative?
We need to mirror the real-world data. If the validation set is different, our model won't perform as expected in the real world.
Got it. So, this data mismatch with nodule locations. Why is that a problem?
Well, imagine you train your model on perfect data, but the real data has slight variations. Your model won't adjust. It's like teaching a kid perfect multiplication, but then giving them problems with decimal places.
So, these coordinates aren't exactly matching, you're saying.
Precisely. The annotation files and candidate files may not align perfectly.
And what's the proposed solution for this?
We're going to fix the data. In real-world scenarios, data often isn't pristine. This is a common problem, and fixing it is crucial.
Why not just ignore the file, though? Seems simpler?
It might seem simpler now, but that would compromise the validity of our training and testing. Ignoring data points leads to a biased model.
Makes sense. So, the solution involves fixing the misalignment.
Exactly. Cleaning up the data is necessary for accurate model performance. It builds reliability.
So, we're not just throwing out data, we're actually fixing it. This is key, right?
Absolutely.
Great, Samuel. Thanks for clarifying. So, now we're trying to use the size to sort and then take samples. Makes sense.
Exactly. We can use size to create a representative spread in validation.
Okay, Samuel, so we're building this function to gather nodule data. What's the deal with this named tuple?
Right. We're creating a structured way to hold key nodule info. Think of it like a container for specific details. It's clean, organized, and keeps our data consistent.
So, it's like a standardized data format?
Exactly. It's vital for training our models. Imagine trying to train with messy, inconsistent data. It'd be a chaotic mess. This named tuple helps us avoid that by providing a clear, unified format.
And why the emphasis on isolating data sanitization?
Well, if you mix data cleaning with model training code, your training loop gets complicated fast. You end up with tons of special cases and checks that clog the code. It makes the training process harder to follow and debug.
So, separate data prep. Got it. What about this caching function?
This caching is super important. We're using this decorator to store results of this function so we don't have to repeat those computations, speeding things up. It's a standard trick in deep learning.
Like a memory shortcut?
Precisely. It's also a smart idea to consider disk caching as well. It can really make training speed fly.
And what's the point of this require on disk bool?
It lets us run with a subset of the training data. We don't need the whole dataset to get started. The require on disk filters out series UIDs not currently available, letting us do quick tests and checks.
That's helpful in these massive datasets, right? It sounds like a good way to test parts of your work with smaller datasets.
It's a great tool for rapid prototyping, debugging, and initial model validation on subsets of your data. We want a good testing ground.
Now, you're merging annotation data with the candidate data. What's that fuzzy matching process you're using?
We're grouping annotations by series UID. Then, for each candidate in a series, we compare their centers. If they're close enough, we're saying, this is the same nodule. If not, diameter defaults to 0. This fuzzy matching handles the occasional imperfect annotation data.
So, a tolerance threshold?
Exactly. We calculate the distance between the centers. If the difference is smaller than a quarter of the diameter, it's considered a match.
Why divide the diameter by 4?
It's a heuristic. We're trying to say, if the two nodule centers are not too far apart, considering their size, these likely represent the same nodule. It makes sense from an engineering perspective.
So, it's a way to compensate for some potential issues with your data?
Exactly. We're being robust. We're not expecting perfect data. If we can't find a matching diameter, it's okay. It doesn't severely impact the model training. As long as we have good representation of various sizes, it's fine. The key takeaway is that this methodology lets us use training data that is not perfectly aligned.
Finally, sorting the data.
We sort by nodule diameter in reverse order. So the largest nodules come first.
Okay, Samuel, we're diving into loading CT scans now. So, what's the deal with these .mhd and .raw files?
Right, Alfred. These are common file formats for medical imaging data, like CT scans. Think of the .mhd file as a sort of header file, containing metadata about the scan, like the dimensions and what to expect inside the raw data.
Okay, and the .raw file is just the pixel data itself?
Exactly. It holds all the information, but it's raw, unorganized. We need tools to interpret it.
So, simple ITK is a crucial tool here, right?
Absolutely. It's a powerful library. It handles the complexities of reading that raw data, interpreting the headers, and putting it into usable Python objects, like NumPy arrays.
And these Python objects, how do they help us?
They let us access the 3D nodule density data. Imagine the data arranged in a three-dimensional grid, giving us precise data.
That makes sense. So, there's this series entity. What's that?
That's a unique identifier for each CT scan. DICOM uses these UIDs, which are kind of like unique names, to track different datasets, scans, etc. Very important for identifying and organizing our data.
And these UIDs, are they always like standard formats?
Not always. They're mostly ASCII characters, but sometimes they might have non-standard characters, especially in anonymized data. So it's good to have libraries like SimpleITK handle this.
Gotcha. So we load them into NumPy arrays. Is there anything important about those arrays that we need to keep in mind?
Yeah, they're three-dimensional arrays. The values represent density measurements at each point. Crucially, the data itself contains spatial information and is implicit. Think of it as a grid of measurements.
So basically, we're converting the raw binary data to data that we can use in our models.
That's right. We're going from bits on a disk to numbers in our program. Crucially, this allows for precise manipulation and analysis of medical images within our Python environment.
That sounds manageable. What about the tip about focusing on relevant data?
It's crucial. Imagine you've got a mountain of data, most of it irrelevant. Focusing on the nodule annotations is important, so you don't get overwhelmed by the unnecessary information.
Makes sense. Any common pitfalls to avoid?
Sometimes people rely too much on third-party libraries. It's good to understand your data's content, but it's okay to use SimpleITK to parse the raw data if you need it.
So, Samuel, we're talking about pre-processing CT scan data. You mentioned Hounsfield units. Can you explain why these are important?
Absolutely. HU are a way to quantify tissue density. It's not just about the raw numbers, right? Understanding the data is key.
Right, so it's not just the bits?
Exactly. Air, water, bone. They have specific HU values. Knowing these ranges is critical for our model.
So, how does that help our model?
Well, without proper scaling, the model might struggle to discern different tissues. Imagine trying to identify a tumor that's near water. If the model doesn't understand the HU values, it might miss it.
You're saying we need to filter out some values?
Precisely. We clip the HU values between -1000 and +1000. We're getting rid of extreme outliers.
Why is that important, though? What are the potential problems if we don't do this?
Unclipped data can mess with the model's training. Things like batch normalization can be skewed by these outliers. Imagine a tiny tumor in a huge bone. The bone will drown out the tumor.
So we're not just cleaning, we're improving the signal?
Yes. It's about making the model's learning easier. Plus, this is a perfect example of understanding the nuances. It's not just about the numbers, it's about the meaning behind them.
This is all very important, Samuel, and definitely helpful. You said that the range of -1000 to +1000 HU is essential. But why specifically for this stage?
See, later on we're adding channels to our data, new pieces of information, and the raw HU values become critical. If we don't account for the difference, these new channels can get lost in the noise.
I see. So the HU values are a critical baseline, but not the sole focus, right?
Exactly. We're focusing on the HU values here because they inform the understanding of the underlying structures, not just as the only values being used. We're removing outliers that don't help our model. Focusing on relevant data means the model learns better, which makes future work easier.
Okay, Samuel, so we're talking about locating these nodules. How does this centering thing work exactly?
Yeah, it's crucial. Deep learning models, they like things to be predictable.
Predictable? Like how so?
Fixed sizes. They need inputs of a particular size. So you take a slice of the CT scan, but you need it to be a certain shape and dimension.
Right, a standardized input. Makes sense. But why center the nodule?
Well, imagine trying to teach a model to recognize a small detail tucked away in a corner of a huge picture. It's like trying to find a tiny red on a giant canvas. You'd have to learn a whole bunch of extra stuff to look in the right place.
So, centering it makes it easier to learn those features?
Exactly. If everything is nicely centered, the model only has to learn the features of the nodule itself. It doesn't have to figure out where to look. It's like giving it a recipe. The ingredient is always in the same place.
That's smart. So, it's about simplifying the training process?
Exactly. Less variation means less work for the model to figure out. It's efficient learning.
Makes perfect sense. So, in practice, what does this centering actually look like?
Imagine you've got a target area for the nodule. Then, you adjust the image crop to fit around it. You get an image with a nodule exactly in the middle. It's all about consistent input. Reduces errors in the model's training.
So, you could have potentially a lot of different potential location issues without that centering.
Exactly. Training a model on varying inputs can lead to false positives and inaccuracies.
That's interesting. What if the nodule isn't in the expected area?
The model will struggle to find it. That's a problem. You might need additional pre-processing to handle those cases. It's a very precise approach.
Okay, Samuel, so we're dealing with patient coordinate systems. Why is this important for CT scans?
Well, Alfred, imagine you're trying to pinpoint a tumor. You need precise location, right? Patient coordinates give you that, but in millimeters. CT scans use voxels.
Voxels? What are those?
Tiny cubes that make up the image. The problem is, millimeter measurements don't directly translate to voxel locations.
So, you need a translator?
Exactly. We need a way to convert from patient coordinates, like XYZ, to array coordinates, like IRC. Think of it as changing languages.
And how do we find that translation?
The DICOM header. It holds all sorts of information, including the conversion rules.
DICOM files? Metadata in their headers?
Yeah, metadata about the scan. It's vital for aligning the patient's real-world position with the digital representation. It tells you how patient left corresponds to a particular voxel column, for instance.
So, the metadata gives the transformation. That's helpful. But why not just use millimeters?
It's not as simple as plugging values in. Voxel indices are discrete integers. You can't have a half voxel,
I see. So, The origin of the patient coordinate system might not match the CT array's origin?
Precisely. They're different. Think of two overlapping grids, one representing the patient, the other the scan.
And these systems are important for broader applications, right?
Absolutely. You could use this for comparing results from different scans. It's essential for consistent measurements and reproducibility.
It's like defining a common ground for these two different worlds. So, Samuel, CT scans, huh?
Yeah, often they're rectangular. Like 1.125 millimeters by 1.125 millimeters, but 2.5 millimeters in the third dimension.
Interesting. So, different lengths in different directions? Why is that?
It's usually how the scanners work, Alfred. Different axis directions may have different resolutions.
Okay, I see. And what about those images? They can look distorted, right? Like squished?
Exactly. If you plot them as squares, you get this odd compression effect.
Like a Mercator projection? A map distortion?
A bit like that, yeah. But the distortion in the CT scan is uniform and linear. You know, like predictable.
So, predictable distortion? How we figure out how much it squishes things?
You need a scaling factor, à multiplier, to make sure the proportions are correct.
Ah, a scaling factor. Important. So, we're not misinterpreting the data?
Exactly. Without that info, you might think the data was corrupted or something wrong happened during loading.
Right. Easy to mistake a squished image for a problem with the data. So how big are these things usually?
Typical CTs are 512 rows by 512 columns.
100 to 250 slices? That's a lot of data points.
Absolutely. And each slice is like 2.5 millimeters thick, so that's a lot of voxels. 250 times 2.5 millimeters. It's a lot of data.
So, roughly 32 million or more data points.
Yeah, you're getting close, Alfred. The voxel size is usually in the metadata.
Crucial. So, how do we get that information? Any example of the code?
There's no code I can provide, unfortunately, but in software, functions like CT_MHD getSpacing can be used to retrieve voxel sizes from the scan file.
Hey Samuel, this chunk is about converting coordinates. It's crucial for medical imaging, right?
Absolutely. We're talking about translating between how we think about things in the real world, millimeters, and how computers store them, voxel indices.
So, you're saying voxel indices are like digital addresses?
Exactly. Think of a 3D image. Voxels are the tiny building blocks. Their addresses are crucial for finding specific parts.
Okay. And why is converting essential?
Well, we need to know the real-world location of a point to interpret it accurately. You have the coordinates in millimeters, and you need to map them to locations within the image array.
So, you're creating functions to do this?
Yeah. We have IRC2XYZ and XYZ2IRC. These handle the conversions.
Can you walk me through the steps in IRC to XYZ?
We take the input coordinates, IRC, then swap the order CRI. This lines up with the XYZ system. Then we scale those indices by the voxel size in each direction. Next, we multiply by the direction matrix. And finally, we add the offset.
The direction matrix? That's interesting. What does that represent?
It encodes rotations and flips. Imagine a scanned object that's not perfectly aligned with the axis. The matrix compensates.
So, XYZ to IRC does the reverse?
Precisely. It's the inverse operations in the reverse order. We subtract the offset, then use the inverse of the direction matrix and divide by voxel size. Rounding and converting to integers are crucial steps too.
I see. So, the voxel size and the direction matrix, where does that information come from?
It comes from the metadata, like the .mhd file. It holds the scanner's setup.
So, it's stored alongside the image data.
Exactly. This helps us translate between different representations of the same object. It's like having a dictionary that tells us how to go between two languages.
And why is using NumPy arrays important here?
NumPy makes these matrix operations fast and efficient. That's important when you're dealing with potentially massive images and calculations.
So, these functions allow us to look at data in real-world coordinates, millimeters, or in the computer's internal representation, voxels.
Correct. We can move between representations. This is fundamental for a lot of medical image processing tasks, like when you're trying to analyze or compare different aspects of an image.
Great. So, by using the metadata from the .mhd file, we can convert between the two systems with these functions?
Yes, you can look at patient data, millimeters, and then work with the data in the computer, voxel.
Okay, Samuel, we're talking about extracting nodules from CT scans. So, you're saying focusing on a smaller area is key?
Exactly. Imagine trying to find a tiny speck of something in a huge pile of sand. It's overwhelming. You need to zoom in.
Right, zoom in like a microscope on a tiny detail. Why does this matter?
Because the volume of data in a CT scan is enormous. Most of that data is not the nodule. We're trying to avoid wasting processing power on irrelevant stuff.
So you're creating a smaller problem. That makes sense. How is this practically done?
We pick a potential spot, a candidate. Then, we extract a cubic chunk of the scan around that candidate. This is a manageable set of data.
So, a zoomed-in picture. How do you pick a size for this chunk?
The chunk size is determined by a width in voxels. We need enough data around the candidate to hopefully encompass the whole nodule. Too small, and you miss it. Too large, and you still waste lots of processing. There's a balance.
How does your extraction code know where to cut out this area? What's the algorithm behind that?
The code uses the candidate's coordinates. Think of it like an address. It figures out the starting and ending points, then slices the 3D data cube.
Interesting. What if the candidate is right at the edge of the data?
Well, that's a potential issue. Our simplified code example skips these edge cases. In real-world use, you'd have to handle those special circumstances to prevent errors.
So, troubleshooting is important. Are there any common mistakes in this process?
Definitely. If the width is too small, you might miss the nodule. Conversely, if it's too big, you're still dealing with a huge amount of unnecessary data. Finding the right width is critical for good performance.
Makes perfect sense. In the code example you showed, where does that fit in this strategy?
That's the getRawCandidate function. It takes the candidate's location and desired chunk width, converts coordinates, and returns the extracted data chunk.
That's a lot of abstraction. Can we see it working with an example?
Smiles, I can't show you the code, but imagine a 3D model, a digital representation of a lung. The candidate is a possible spot within the model, and the getRawCandidate function is like a digital scalpel, precisely cutting a cube of data around that spot. It also gives us a reference frame for the extracted cube, so we can use it in a model correctly later on.
Okay, Samuel, we're diving into custom datasets now. This is cool. So, we're building our own Luna dataset. What's the key difference between this and using pre-built datasets?
Yeah, it's crucial. Pre-built datasets are great, but we're crafting something specific to our CT scan data. This way, we control the pre-processing.
So, we're normalizing the CT nodules. Why?
Normalization is vital. Think of it like leveling the playing field for our model. Imagine different CT scans with different intensity ranges. Our model needs consistent data to learn properly.
Right, makes sense. And the flattening? That's a step to make the data usable, right?
Exactly. The data's raw form isn't something our model understands. Flattening helps in processing individual samples, no matter the CT instance they come from.
Interesting. So, the __len___ method?
It's simple. We return the count of samples. Crucially, it needs to be a constant value after initialization.
And _get_item__?
That's where the magic happens. It's like getting a single sample. Takes an index, and it returns a prepared training sample.
How's it prepared?
It takes the raw data, manipulates its shape, and constructs the tensor for our model's input. We need precise data types too.
Like turning a raw CT scan into a usable tensor.
Precisely. And it also handles the classification output. Crucially, the model needs a target for each instance, nodule or not.
So, that output is carefully structured, too, with a tensor for each class?
Exactly. Our output is structured, as nn.cross-entropy loss requires specific formats for multiclass prediction. This is key to accurate model training.
And the resulting tuple? It's 4 items, right?
Yep. For items, the image data, the classification target, and the unique ID, along with the center of the nodule. It's a complete sample.
I see. This is helping me understand the pipeline. Any potential issues with these steps?
Absolutely. Issues arise if _len___ isn't a fixed value, or if __getItem__ doesn't produce valid data for all indices. Mismatched data types or incorrect dimensions can also cause errors.
Thanks, Samuel. That gives me a good overview. This is a crucial step in preparing our data, so we can train the model efficiently. So, we're talking about caching CT scans. Why is this crucial for performance?
Yeah, it's a big deal. Imagine reading a whole CT scan every time you need a small part. That's super slow. Caching lets us quickly grab parts we've already looked at.
Okay, but how does this caching work? You mentioned a function, getCTRawCandidate. Can you explain that?
Sure. GetCTRawCandidate is like a shortcut. It gets a CT scan, then grabs a specific part. We cache that whole process. So if we need the same part again, we just pull it from the cache instead of reading it from the hard drive again.
So, a little like a library for parts of the scan?
Exactly. The function you're seeing there, getCT, is designed to just get the CT scan object. Then, it's the getCTRawCandidate that actually extracts the part we need. Crucially, we also cache the result of getCTRawCandidate on disk, not just the getCT result.
Caching the result of getCTRawCandidate? Why store it on disk? Why not just in memory?
Well, memory is limited. If we had lots of scans, keeping every part in memory would quickly use up available RAM. Storing on disk allows us to handle many more scans.
This disk cache sounds promising, but what if we change the functions? Won't that cause problems?
You hit on a good point. If we change the functions that extract the parts, the cached values become useless. We need a way to clear the cache if the function definition changes. That's why we store the cache in data_run_version/cache.
So, this caching system helps a lot with performance. But it also requires some care if we change the program or how the scans are read.
Precisely. It's a delicate balance between efficiency and robustness. And we have to make sure we clear out the cache if the program changes significantly.
Is there a trade-off involved? What are the downsides of this caching approach?
Absolutely. The cache needs regular maintenance. If functions evolve, it needs to be cleared. Also, keeping everything in the cache can potentially slow down other things in the system if you're not careful.
Interesting. So we're really talking about a trade-off between speed and maintainability.
Exactly. It's a classic software engineering problem. We need to carefully consider the trade-offs between speed and flexibility.
Okay, Samuel, so we're building a dataset. How does this validation set work exactly?
Yeah, crucial step. We're splitting the data. Every 10th sample goes into the validation set.
Every 10th? That's a pretty specific rule. Why not just randomly select?
Well, it's a stratified sampling method, often better for imbalanced datasets. Imagine a dataset where most cases are healthy, and only a few are diseased. Random sampling might end up giving you a completely skewed validation set, all healthy, no disease samples, making it useless for evaluating the model's performance on the diseased cases.
I see. Makes sense. And this val_stride parameter, what does that do?
That's just a way to control that every 10th sample selection. You can adjust the stride, for different sized data chunks.
Right, flexibility's key. What about this isFLSet_bool parameter? How's it used?
It lets us choose. If set to true, the code returns only validation data, false for training data. If it's none, the whole dataset is returned.
So a toggle, essentially, for a filtering function?
Yep, controls what part of the data we pull out. Super useful for quick checks or specific analyses, like looking at only the validation data to debug a potential problem.
This is good. So this series_e parameter, what's that?
It's a helpful feature for narrowing down our dataset. If you provide a series UID, it only selects the nodules from that specific CT scan. Great for focusing on individual cases or problematic scans.
Makes it easier to debug, right? Or see if there are differences between series.
Exactly. It helps isolate issues without processing the whole dataset. And copying the list? Why do we need that copy?
Sometimes when we're manipulating data, if we don't copy the original list, any changes we make in our calculations might affect the initial list. A copy prevents unintended changes to the original data, preserving the integrity of the dataset.
Exactly. Using copy.copy ensures the original candidate info_list stays unchanged. Important for keeping track of data.
Okay, Samuel, so we're talking about splitting data for training and validation. How important is this exactly?
Crucial. You want both sets to reflect the real data.
Right, but why?
If your training set doesn't represent the variations, your model will struggle with unseen data.
So, like if you train a model on sunny days, it'll fail in the rain?
Exactly. And a bad split can introduce biases.
So, what are the bad splits?
Well, one is where the training set contains hints about the validation set, like using overlapping data points.
A leak, you mean?
Yeah, a leak in the training set.
So, how does this code handle the split?
The code partitions a portion of the data into a validation set. It's like setting aside some of the samples for testing later.
And how is the size of this validation set decided?
It's controlled by dividing the total dataset, kind of like setting a percentage aside.
And there's something called val_stride?
Yep, that controls how many data points are skipped to create the validation set.
So, if val_stride is 2, every other data point goes into the validation set?
Precisely. The code makes sure the split is accurate, without duplicates.
Is there any check on the resulting validation set? Are there enough data points in it?
Yes, there are assertions to ensure that the list hasn't become empty. It makes sure validation data exists after the split.
And how important is the order of the data?
The order of the data is important, especially if we want to keep patients from being in both training and validation sets. The candidate information must be sorted, so we're always guaranteed the same sort, to keep things consistent.
Why is patient data important here?
If you need to make sure patients aren't in both training and testing, you need a structured way of organizing that, making sure it isn't confusing the model.
So, it sounds like there's an importance to the sorted order.
You bet. Without it, this approach won't work as intended.
Alright, so how about these example snippets?
These example snippets give us a look at a real-world dataset. It shows the distribution of diameters and gives us insight into the data. This helps spot possible problems or assumptions early in the project, potentially saving significant time later.
That's super helpful. Thanks for walking me through this data split process. Okay, Samuel, so we're looking at visualizing data. Crucial step, right?
Absolutely. Visualization's key to understanding your data. Helps us spot patterns, outliers, and just overall weirdness.
So this rendering stuff? Can you break that down?
Rendering means creating visual representations, like images of your data. Think of it like taking raw numbers and turning them into charts or graphs.
And why is this important?
Well, seeing your data visually is invaluable. Imagine finding noisy samples. It's easy to spot in a graph. You wouldn't get that directly from numbers. Or a weird sample that seems different. You can spot that visually right away.
So, the code snippet hints at using this matplotlib thing. What is that?
Matplotlib's a popular plotting library in Python. It's super powerful for creating plots and images. But it's a pretty sophisticated tool. Lots of options for making cool visuals. We don't get into all the specifics, but you can certainly fine-tune your visualizations with it.
It sounds like visualization isn't just about pretty pictures, though.
Exactly. It's about insight. Spotting unusual samples, figuring out how different samples relate, noticing trends. It can give you hints that even advanced statistical analysis might miss. It's like you need those graphs to interpret these complicated data samples.
Interesting. In this code example, it shows us some specific functions, like find nodule samples and show nodule. What do those do?
Find nodule samples looks for certain types of samples that we're interested in. Crucial for identifying what's relevant in the data. Show nodule creates the visualizations for these samples, showing us different slices, like from a medical image or something similar.
Okay, so it sounds like this isn't just general plotting. It's focused on a particular dataset type.
Yes, definitely. This is focused on medical image data, specifically lung nodule detection. The specific way samples are ordered is important for reproducibility.
Got it. So this data visualization is a critical step for understanding complex medical data sets. What are the potential pitfalls in this process? What could go wrong?
Well, there's always the challenge of choosing the right visualization methods. The wrong graphs can mask or exaggerate patterns. Another thing is, what if you don't have enough samples? Then your visual representation won't be very reliable.
Smart points. Thanks, Samuel. So, we've transformed our medical images into tensors. Big deal. But why is this crucial?
Well, Alfred, it's like translating a foreign language into a universal code. PyTorch and other machine learning frameworks really only understand numbers.
Right, I get that. But how does this translate to our project success?
It unlocks the door to applying powerful deep learning models. Think of it as setting up your computer for a complex calculation.
Okay, but what about the caching and data splitting?
Those are super important design decisions. The size of the inputs, how quickly we can access our data, it's all intertwined. A well-designed cache can make training lightning fast.
So, bad cache design could slow things down?
Exactly. Imagine trying to build a house with a supply of bricks that's unreliable.
Makes sense. What about the training and validation sets?
Splitting the data is critical. You need a training set to teach the model and a validation set to see how well it generalizes to unseen data. If your splits are off, you might end up with an overfitted model that performs poorly on new cases.
Overfitting, you say?
Yeah, that's where the model is too focused on the training data. It memorizes it, but can't adapt to new information.
It's like a student who only studies the questions from the old exam.
Exactly. We need a good balance.
So, revisiting these decisions later is key?
Absolutely, especially when it comes to real-world projects. We don't always have all the answers.
That makes perfect sense. And we'll see all these things come together even more in the next chapter. Great.